And we're live.
We are live, okay. All right. Thank you everyone for coming. I got a brief introduction. Welcome to Toronto Pro-Mongers and our guest speaker, William Stevenson from Boston. He'll be giving his talk, Where's My Data Analyst? So William started on the business side of MaxMind and moved to development over 2 years ago. Recently he's helped develop a machine learning platform to predict risk of various components of an e-commerce transaction. His code will touch hundreds of millions of transactions per year with a sub-second response time. However, he was not formally trained in either software engineering or data science. When his current project started, he was at a loss for how to understand machine learning and how to use it in the real world. After becoming frustrated with a massively open online course, he turned to machine learning with R and was able to get up to speed quickly. He thinks others are in the same situation and would like to share what he's learned so you can get going quickly. And MaxMind is where our speaker, as well as Olaf, work. It is an industry-leading provider of IP intelligence and online fraud detection. MaxMind provides IP intelligence through the GeoIP brand. You've probably heard of GeoIP if you've done any web development at all. Over 5,000 companies use GeoIP to locate their internet visitors and show the relevant content ads, perform analytics, enforce digital rights, boo, and efficiently route internet traffic. Businesses can obtain additional insights into their customers' connection speeds, ISPs, and more using GeoIP data. Want me to read the whole thing?
No, just whatever. You can definitely make it more concise. It's a bit of marketing speak in there. Just in addition to geolocation, we do fraud detection.
Okay. So most of the people that work for MaxMind are telecommuters. They are based out of Waltham, Massachusetts. But as you know, Olaf has been working with them for a few years now. It's been a few years, Olaf? Mostly?
Yeah, it's been about 2.5 years now. We've got another person from Toronto starting, I think, next week, and a fellow from Mississauga starting the week after that. So.
Interesting.
Yeah.
Cheaper health benefits or something, or? No?
It's actually the way the U.S. tax law works. It's easier to hire people in Canada than in a lot of the states.
Really?
Yeah.
Weird. All right. Well, with that, I want to thank William and.
Great. Dave, thank you for introducing me. Thank you, Toronto Pro-Mongers, for having me. I'll begin sharing my screen. There'll be a bit of a loop for a sec. Okay. Do you all see my screen okay?
Yep.
Okay, great. So, Dave, thanks for the introduction. The title of my talk is Dude, Where's My Data Analyst? It's a quick start guide to using machine learning in a real-world environment. So Dave told you a little bit about myself. I'll tell you a little bit more, and then I'll give some context for how I got into this. I wanted to be a computer science major, but ended up majoring in philosophy. The language that they taught in, went to Princeton, the language they taught in was C, and I couldn't malk my way out of a paper bag, and I had no concept of what I was really doing when I was allocating memory. So in terms of the way I think, I'd much rather have learned machine architecture and assembly language before getting to C. So maybe if I'd studied a generation or two ago, they would have done it that way. But it just didn't make sense to me why things were going wrong when I was core dumping. So didn't major in computer science, majored in philosophy, which I liked, but the itch to program always stayed with me. So I was on the business side of MaxMind for a while. I left for a couple of years to help a doctor's office get ready for an electronic health record system. And then when that was finishing up, I was looking for something else to do, and a small door opened up at MaxMind to come on board as a data analyst and software engineer. So if it wasn't for the previous relationship, that door never would have opened. My resume gave no indication. This was something that I could do, but it was something that had stayed with me for at least 15 years and something that I'd always really wanted to get a pitch to swing at. So anyway, I was able to convert that into a full-time position, and I really liked the way software engineering combines both sides of the mind, the way it's both analytic and creative. And a lot of my work began with sort of reviewing the transactions that the computer couldn't understand. So we have a fraud detection service and it screens millions upon millions of transactions, but we do review a portion of those. And as I got to see some patterns, I was able to teach the computer how to see them. And then MaxMind undertook a project to begin using machine learning in the scoring that we return. And as I wanted to learn more about this, I turned to a MOOC, and I was very excited to take it, but as I got into it, I realized that I didn't have the prerequisites for it, which is fine, but I was really frustrated also because the professor had billed the course as any diligent student can learn this, anyone who applies themselves can get through the material. But later I looked at the fine print, and it recommended linear algebra, Bayes' theorem, and others. So it was sort of frustrating that they billed it one way and it turned out to be another. So eventually a colleague recommended the book Machine Learning with R by Pact Publishing, and for me this was a much better way to get going. In about 3 weeks I was able to work through the core of the book, and as I worked through each chapter I also applied that algorithm to the problem I was trying to solve at work. And so within 3 weeks I was able to work through the core, and then spend another 2 sort of really evaluating the final candidates before putting one forward for integration into production. And as I've talked to other people, it seems like there's sort of this very steep sort of esoteric learning curve around machine learning, and it definitely is good to understand the math behind it, but I feel even if I had gotten through the whole 12 weeks, there's a bit of a separation between what I needed to learn in the real-world environment and what they were teaching in class. So my hope is that by having to teach this to myself, I'm in a better position, or hopefully a decent position, to teach it to others, and that I'd also like to share a little bit what I've learned so that other people can get going quickly. And my hope is that by the end of this presentation, you'll have a sense of the territory around machine learning, and also a sense of a compass as to how to navigate that territory. And one of the points I really want to make is that the algorithms are important. There's a lot going on around the algorithms that really seems to get lost in the discussions on machine learning. So hopefully by filling in that context, you'll be able to orient yourself much better when you actually have to choose algorithms and move in that direction. So for those of you who aren't physically present today, presented to Toronto Pearlmongers. So there'll be 3 main parts to the presentation: preparation. There's a bit of a reverb now.
Oh. Let me track that. I'll mute.
Okay, great, thanks. Preparation, algorithms, and then also growing. How do you as an individual get going with machine learning? And so in terms of preparation, there'll be 3 main sections, starting with a question, defining features and the data. We'll move into this right now. So let's begin with a question. As I mentioned, I was a philosophy major and I like questions. So what is machine learning? And etymologically, there's 2 parts to it: the word machine, which in this case is just a computer, and learning, to follow or find the track. And one thing I actually really did like about one of the MOOCs was that the teacher called it learning from data. And I thought that that was a great title for a course, in the sense that normally, like when we're working with the computer, it's been a tool, whether it's been an abacus or sticks or beads or whatever we've used historically writing to do math. The computer is just the most contemporary tool to help us do math. But usually it's been more where we're already know what we want to do. We want to take an average over millions of rows, and the computer enables us to do that in a way that would take a very long time if we did it by hand. But with machine learning, the computer itself is actually trying to understand the relationships in the data, and it's telling us what the relationships are rather than us using it in a more directed way. So there's a bit of a corner that's being turned in modern times with machine learning. So my concise definition is just a process whereby a computer comes to understand information. And one of the biggest questions is, where do you start? And how do you get going? So traditionally, again, it seems like people oftentimes start with algorithms, and a common question is, what's the best algorithm? But in the same way you might ask, like, what's the best car? You really need to say, what's the best car for what purpose? Are you commuting? Are you hauling, heavy goods? Are you going cross country? What are you really going off-road? How are you using that car? So there's also usually an organization or an individual that wants to use this, and there's a larger context in which it sits. So for me, a better place to start is actually right here with a question. And there are lots of different kinds of questions that you can ask. How risky is this e-commerce transaction? Will it rain tomorrow? Does this patient have cancer? Is this a good lead for our company? or which ad is this visitor most likely to click on? These are all very relevant questions to machine learning, and I think this is a great place to start because it'll actually, as you'll see in the presentation, it's sort of like a seed growing. It leads from one step into the next. So in our case, let's imagine a vineyard, a vinter, and called Chateau Gusteau. And Chateau Gusteau wants to know, how will this wine be rated? So what are they going to do? The answer in machine learning, I'd like to give you some terminology so you have a working knowledge of it. The answer to the question that you're asking is called your target. Sometimes there are different names for it besides target. Sometimes it's called a label, but we'll just use the word target. So the answer to the question that you're asking is the target. In step 2, you define what's called features. And if the target is the dependent variable, the features are the independent variables. They're what the target is a function of, or what it's an expression of. In our case with the vinter, things like acidity, possibly marketing, sugar content, age of the wine, density, age of the vineyard, sulfur content, or weather. There are a lot of different factors that could go into the wine, and it's very important that these capture the target value. So mathematically, target f is a function of features, y is a function of each of these individual ones, and when you add them all up, you get your whole data set. And so normally, when you sort of think of a function, you sort of go from the function to the data, but in this case, we're almost going backwards. We're trying to develop a function that fits all of the features that we've defined. And ideally, your features are orthogonal to one another, that you don't really want too much overlap between them, so that if you say you're predicting the weather with the rain, and you have humidity and another feature that's closely related to water content, that's not so helpful. You want to ideally have them be independent. So step 3, after you've defined your features, you actually want to gather data. And in this case, this will be developing a training set. We have the tag, the name and the rating, and then the actual features themselves. So the name is called the tag. The rating is our target, and the tag is useful in debugging. Say something's, we got a particular one wrong or we got it right. The tag helps us. We go back in and try and understand what our model is doing and where it got it right and where it didn't. And then these other ones are called the features. Then we have a bunch of each individual row we'll call an example. And what we're trying to do with this training set is to build a model. We're trying to create a function such that when we see a new example, it can make a prediction. So in our case, Chateau Gusteau, there's this question mark down here, and they're wondering what that wine is going to be rated. So in this case, maybe it gets an 85. Now, there are a lot of different ways to do this, and I'd like to go on a conceptual level how some of the different algorithms work to create that function. So these are our data points. So one thing we can try and do is to create an equation that fits this line, and we're trying to reduce the distance between each point in the line to minimize that error. So, in a two-dimensional space, or y is equal to mx plus b, just slope-intercept. So when a new point comes in, we're wondering what's it rated. So it'll have a value on the x-axis, and the line is going to map it to the y-axis. So this is called regression. Another way to do it, after we get our new points, we have a new point coming in, and we're wondering what it's rated. So there's this expression in Spanish, tell me who you walk with, and I'll tell you who you are. You look at the other points in the vicinity of the one that you're trying to, the new example, and you use those to give the value to the one in question. This is usually called nearest neighbors. Another way is to look for homogeneous groups within the overall data set.
Just to clarify for someone who's a little dim like me, each axis, you've got two axes here, but each axis represents a feature?
Yeah, yes. In the first example with the regression, Dave, I'll go back to that first slide. So thanks for asking too. So in this case, there's really just one feature, the x-axis, and that's mapping to the y. So it could have n dimensions. Usually it's multidimensional, but just in the limitations of the presentation, I just did it in two. But in this one, there's one feature x, and it's getting mapped to y through the equation. Right there, yeah, right there. And then in the next one, this one, I'm assuming two features, x and y, and I sort of the target value is the color. So I sort of tried to give a third dimension to the graph by using color. And in this case, it's probably a class like yellow or blue or A or B or spam or ham, as opposed to a numeric value in the other one. But yeah, in this case, there's two features, and the color yellow or blue is the target. Does that answer your question, Dave?
Yeah, it answers mine. Did anyone have any clarification they wanted? No? We're good.
Okay, great. Yeah, and keep asking questions as I go. That was great. So. Okay, so another way to model the data is to try and break it into homogeneous regions. So right here, the top area, the top two are blue, and the bottom area is sort of still heterogeneous, but the top part is pretty consistent. Then we try and find the next split to give the greatest homogeneity. Right there, so you see the left one's a little bit better, only 5 blues and 2 yellows. Then we go right there, we have a completely homogeneous zones. There, there, there. So this is actually called a decision tree. I'll explain it a little bit more in a sec. But a new one comes in, and it's in the box with the other yellow, so that would probably have been given the class of yellow. So in that case, we'll call it yellow. As I mentioned, this is called a decision tree. And there's a guy named Ross Quinlan out of Australia who's done most of the work on this. There was a statistician named Leo Bryman who did some work too. But anyway, Quinlan, his methodology is to use information theory. Has anyone heard of Claude Shannon? Anyway, Shannon used entropy to measure the amount of information in messages, and Quinlan uses entropy to figure out how much various features carry about the target value. And it's actually a very simple algorithm, and it's used recursively, so it's called a divide and conquer. One weakness in it is that once it's made a division, it doesn't really go back to figure out if it was optimal, so it's possible for there to be suboptimal ones, but they can handle a lot of data, and they're relatively compact. So this is called a decision tree because it actually stores the splits in a tree structure. There's also probability, ways of doing probability. So if you have the probability of A, the probability of B, and we have them both occurring together, what does that say about our target? A classic, this is actually Bayes. There's the full Bayes and naive Bayes. You probably hear about both of those. And a classic example is like spam and ham. So if an email message has the word Viagra in it, it has a probability of being spam. and it has the word free in it, it also has the probability of being spam. But what's the probability if it has both spam and free in the same email? Bayes' theorem explains how to combine those probabilities together to get the overall probability of what you're trying to predict. So another way to do it is to see if these spaces are linearly separable. So we draw a line like this. You can see the ones on the right are fairly yellow, the ones on the left are fairly blue. And this is actually called, so when we have a new one coming in, we're wondering how it's classified, and it will go on the side with the blue. Because there's more blues on the side that it's on, that's what we'll classify it as. This is called a support vector machine, and there's pretty heavy math behind it, but basically the support vectors, you sort of take the ones that are closest to either side of the line, and you sort of use those to evaluate if the line that you've given separates them in the best way. So part 2, actual. What are some examples of these algorithms? Regression, there's one called Vopal-Rabbit, and there's going to be a blend of algorithms and particular implementations here. So Vopal-Rabbit was written by a guy named John Langford out of Microsoft Research. It's a very powerful regressor, and it can handle terabyte data sets. So it's created for, it assumes out of core, so it can handle very large data. Listen to one of the talks that he gave online, and he really cares about code quality. I think I want to say it's only 2,600 lines of code, and he'd rather have it be smaller than larger. So it's a pretty incredible tool if it's right for what you're doing. Also, most any machine learning package is going to have regression in it. Weka, I don't know about waffles. Scikit-learn, CPN, and there is some stuff on CPN, not a lot, but there's some regression on CPN. In terms of nearest neighbors, the classic one is k nearest neighbors. K refers to the number of points around the one in question that you're trying to use. So in the example I gave, I think I used 5 points around the one in question. So in that case, k would be 5. And there's a period of optimization to sort of try and figure out which ones are around it. Again, most any ML package, it is on CPAN. And then also, this is one you could write yourself. It's not, in modern times, more advanced algorithms have surpassed it. But in terms of a learning exercise and getting going, this is one, if you understood sort of the math underneath it, which isn't too hard, that you could actually implement yourself. And that could be a good exercise. So decision trees in terms of algorithms, C45 and C50 by Quinlan. Actually created another one called Cubist. And it's like a hybrid between regression and decision trees. Rather than having a predicted class at the leaves, it actually has a regressor just for the examples that reach it. J48 is a Java implementation of C45. It's in Weka. And then there's M5 Prime, which is sort of a sister to Cubist, someone else's version on it that may or may not do better depending on your situation. Cart by Bryman, Ripper, people, Quinlan, Bryman, Yang and Wooden did M5 Prime. Sources, standalone, R, and Weka. Bayes, probably most machine learning packages will have it. CPAN. And then also, if you did understand the math, again, this is one you could probably implement if you understood the math behind it. Support vector machine, libsem, SEMlite, Shark, dlib, R, Weka, CPAN. And the one thing that's important here is a lot of these tools, even if they're not written in Perl, they often have Perl bindings to them. So that's going to be a consideration. You don't have to necessarily ask whether or not it's written in Perl, but if it has Perl bindings, that can be enough. So part 3. Practical. How do you choose an algorithm? And I think this is really important for anyone that's actually trying to get out of an academic setting and into the real world. So we're actually going to go back to the data. And one of the main questions you want to ask is, what am I trying to predict? So is the target a class? Is it continuous? Those are going to greatly influence what algorithm you choose, because some of them can only predict a class, and some of them are, like regression, can only predict a number value, whereas like nearest neighbors can only predict a class. So knowing what you're trying to predict is really important in choosing an algorithm. So you also want to look at the shape of your data in terms of trying to get a sense of what the distribution is like. Is it normal distribution, or is you sort of have values that are skewed to one side or the other? And then when I say shape, I also mean like what do you expect your target to look like? If you look at regression, it sort of assumes a linear line. If you look at something like a support vector machine, it assumes that they're linearly separable. And there are various tricks as you get more advanced in terms of transforming the data that's not so perfect, but the more you can understand what your data looks like, the better time you're going to have actually choosing an algorithm. So again, here we have classed versus continuous. Another important part is scale. If we have two sets of data, you can see that scales are vastly different here. And for a lot of algorithms, you need to have them all be on roughly the same scale. There's a bit of finagling to figure out how to do that. How do you transform? If you think of the two axes, you would sort of, in order to fit a line to it, it matters how it's scaled. So depending on how you do this, depends on how well the machine can understand it. And however, like with decision trees, for example, they're what's called non-parametric. So it doesn't actually matter how you're scaling your data. So it can actually be a little bit quicker to implement because you don't have to worry about that aspect of it. But knowing your data is important here and having a sense of what the scales are like. Another big question is how much data do you have? Do you have a little bit of data? Do you have a lot of data? If you're working in bioinformatics, oftentimes that'll need to have been done by hand. So you'll probably have maybe samples in the thousands or 10,000s. If you're doing something that's online based or that's generated from computer generated data, you're going to have a lot more data. And some algorithms can handle a lot of data. Other ones are going to take a lot longer to train and won't necessarily be as suited for this. I'm actually not even mentioning neural networks in this because I found that they were very finicky and they didn't handle lots of data very well. So in quantitative data, I mean both rows and columns. Another big, huge question is how does it handle sparse data? Oftentimes in the real world, we don't have all of our values filled in. We'll have missing values or undefined values. And there are always tricks on how to do this. You could dummy code it. You could use the median value. But you really need to think about how you're going to handle, if you have sparse data, how are you going to handle it? And for example, with Quinlan C50, that's actually a way to build a model with missing values and is able to predict with missing values. If a new example comes in and a particular feature is undefined, and that's the decision point, they'll send the example down all branches of that node and amalgamate the results. So it's he actually did some research on how different methods of filling in dummy values affect the predictive ability, and dummy coding was not the greatest way. So if this is sort of a big aspect of the data that you're receiving, it's important to think through this question. So I've created a little bit of a chart to run through some of the different algorithms and how they handle things. With a lot of this, there are different tricks. So even if it predicts, like for example, the target is a class, but you want a number, well, oftentimes the algorithm can predict the probability of that class. So it might say spam, but it might also be able to say 75% spam. So even though it's predicting a class and you want a numeric value, as long as that 0 to 100 or 0 to 1 is okay for you, you can still use that algorithm. And then again, whether the features are continuous or classed is important. Do they need to be scaled, and how does it handle undefined values? So,
got a question here in the crowd.
Yep.
Yeah, the footnotes, of course, I'm dying to know what the footnotes are. There we go. Thank you.
Okay. Yeah, so I'll run through those. So in terms of one, those can get the probability of a class. With decision trees, model trees have regressors at the leaves, so that can sort of there's a variation in the decision trees that can actually predict a continuous value. In terms of continuous features, can be binned. So say for example, it needs a class, but you have 0 to 100. You can split it into 0 to 10, 10 to 20, 20 to 30, 30 to 40, so forth, and that can be another way to sort of take a continuous feature and convert it into a class. You can also feed Bayes a distribution curve. and then undef values can be dummy coded. But again, you sort of one thing that's hard is if your data is changing over time, does your dummy coded value need to change also? I said no for big data for SVM. People might take issue with that. It probably just depends on how much data you have. But in my experience, it was taking a lot longer to train than some of the other algorithms. So for me, I put a no there, but that could be contentious. Trial. And actually, as you get going, nothing actually replaces rolling up your sleeves and actually beginning to work with the algorithms. And this is where, find a good book, join another meetup, download some software, participate in forums or Kaggle competitions. This is where sort of the traditional learning tools I think are going to be the most helpful as to what the algorithms are and how to get going with them. So again, I found machine learning with R very helpful because one of the things the book does really well is explains the long way before it does the short way. So even if you're not going to use the long way, it helped me sort of having seen it done once, so I could sort of lock it up and throw it away. And then also most likely you'll be probably working on a platform. The two major ones are R and Weka. R is more for statistical computing. Weka is more for machine learning. They're kind of converging. Weka is written in Java. R is actually a language unto itself in addition to sort of a platform. So it was a little funny to get used to, but once I got into it, I actually liked it a lot. And also I want to say a word about Kaggle competitions. One other thing is, you often need data. Kaggle is great because it gives you a data set. There's forums where people are talking about how they're solving the problem, and there's sort of a social side to it also, and a bounty at the end if you do a really good job. So I found Kaggle to be a great place too to begin to learn how to do this. Error. Stephen Covey in the book 7 Habits of Highly Effective People, he talks a little bit about starting with the end in mind. And it's really important to think of how you're going to evaluate how well your model's doing, particularly if you have two different candidates and you want to sort of figure out which one's better. How do you actually evaluate how well it's doing? And it depends on whether you have a class or a continuous target. So we're going to run through an example of how to look at how we're doing with a class-based one, and then we'll jump to a continuous target. So we'll do an example of spam and ham, and we're going to call spam positive. We're going to call ham negative. So on the left, the rows are the actual values, and the columns are predicted. So if our actual value is ham and we predict ham, we're going to have two minuses. That'll be called a true negative. If our actual value is spam and we predict spam, that's going to be there called a true positive. If our actual value is spam and we predict ham, that's a false negative. And if our actual value is ham and we predict spam, that's a false positive. So let's run through some predicted. So this is a sample set of predicted values. Our label is spam. We predict spam. Positive, positive, true, positive. We predict spam. Label is spam. We predict spam. True, positive. Ham spam. False positive. True, positive. True, negative. False positive. False negative. So how did we do? 7 examples, 4 correct, 57% accurate. But is that the whole story? The confusion matrix can help us dig deeper. So we had one actual ham. Of the actual ham values, we predicted ham correctly once and spam twice. So there were 3 actual examples of ham in the training set. So we're 33% accurate predicting ham. And with spam, there were 4 examples, and of those, we got 3 right. So we're 75% accurate predicting spam. But that doesn't, it's sort of getting a little bit to what happened, but it's not the whole story. But wait, there's more. So if we go the other way vertically, we predicted ham once, and we're correct. And when we predicted ham one time, it was actually ham, and one time it was spam. So of the times we predicted, 50% of those predictions were correct. In terms of spam, we predicted 5 total times, 2 of which were incorrect, and 3 of which were correct. So 60% of the spam predictions were correct. So even though we're 75% accurate, of the predictions we made, only 60% of those are correct. So what's actually going on here? Do you guys? Oh, there's a question for the audience. What do you think's going on with our spam filter?
So there was one, it's underperforming.
Yep. And how is it underperforming? Like if I said to you every day that it's gonna rain tomorrow, I'd be right the number of times that it rained. But what would you? How trustworthy would my predictions be?
A lot of baffled faces.
My conclusion is that our spam filter is too aggressive. It's marking things as spam too aggressively. So even though it's 75% accurate, and a lot of the spam examples in the training set were correctly marked, of the times it says spam, it's actually only getting those right 60% of the time. So it seems like it's saying too often it's spam when it's not. It needs to be a little more sensitive there. So in terms of continuous, we'll work through an example with that also. Mean absolute error, root of the mean squared error, we'll work through an example. So the target, if we said 87, the prediction was 95. The difference between these is 8. The absolute difference would be 8. And if we squared the error, we get 64. I'm not going to speak all of them, but we'll sort of go through. Does anyone have any questions about this before I sort of jump to the math to how to calculate the error? It doesn't have to be. I just want to make sure what I'm really asking is, does the last and next to last columns make sense to everybody?
Everyone looks comfortable.
Okay, great. So if we add up the absolute error, we get 13.2. We add up the square there, we get 70.74. If we take the mean of that, 189, 10.9, and then if we take the root of the 10.9, we get 3.18. So the mean absolute error is 1.89, and the root of the mean squared error is 3.18. So they're just sort of two different ways of measuring the error. And generally, because you're squaring the error, it's going to penalize outliers a little bit more. So you can see, like in the first row, when we're off by 8, that leads to a 64. However, if it's smaller, then the error isn't as much. We are taking the root of it at the end, so that can counterbalance it a little bit. But it also depends on the scale of your values. If all your values are between 0 and 1, and you're scaling them, that'll sort of make everything kind of small. So neither of these are perfect, and there are other ways of doing it also. You have other choices. Kappa. The other thing is Kappa tries to look at if sometimes, like in science or medicine, they'll say this test is like 99.9% accurate at predicting a particular disease, but if the disease only occurs 99.99 in like 0.0001% of the population, like a 99.9 is actually horrible. It's worse than just predicting. It's worse than just predicting that they didn't have anything wrong with them every time. So Kappa is trying to look at how much better is the algorithm doing than just sort of predicting the most common value. Correlation, how strongly correlated is your target value to the predicted target value to the actual one. And then area under the curve. That's another one. So now another huge question in terms of choosing an algorithm is the integration side of it. And in terms of integration, what language are you programming in? I'm going to run through a couple of these and talk about them as a group. So, most of us are programming in Perl, so that would be, our language. Another question is, what kind of API does the package or the algorithm have? And you might ask, how is an API different from the language? Well, some actually allow you to communicate with them over HTTP. And if it does allow you to do that, it almost doesn't matter what language you're using, because most languages have web bindings. So you could put it behind Plaque. You could do whatever you want to, and sort of integrate into a Perl environment very easily if it lets itself be called this way. Another huge consideration is, are you trying to predict in batch, or are you trying to predict continuously in an online environment? And there are two huge considerations here. One, if it is continuous, your model probably needs to live in memory, so it can't just sort of, it has to be able to persist. And then secondly, not only does your model need to persist, as new data is coming in, how do you update your model? So that's, and then there can even be feedback loops where if you're predicting values, and if you're using the values that you predict back into your training set, you're sort of creating a feedback loop. So you sort of need to think of how you're going to update your model if you're using it continuously. And then also, if you're using particular bundles like R or Weka already, that might influence which way you go. And one nice thing also about using something like R or Weka is that once you've integrated it, and you want to add, if you want to add another algorithm, most of the hard work is already done. So it's sort of easy to add new components to a system. On the other hand, it can add a layer of abstraction and complexity that you might not need if there's just sort of one that seems to be working pretty well for you. So one of the biggest questions is, how do I begin? How do I start growing? And one of the things that I think really benefited me at MaxMind was, having sort of worked as a data analyst first, I was familiar with the data. So when it came time to sort of begin to work through algorithms, I already had a sense of what I was working with. And I think all of us have started to program one way or another, and one of the big questions is, how do you start programming? Well, it's sort of the same answer. You learn to program by programming. I think one of the ways you learn to analyze information is by analyzing information. But in the same way this presentation said to start with a question, I think it's really important to ask yourself, what questions am I interested in? What kind of questions do I want to answer? For some people, it might be bioinformatics. For some people, it might be fraud detection. For other people, it might be financial analysis. It's up to you what you're interested in. But I think out of those questions flow the data. Out of the data flows the algorithm. Out of the algorithm flows the integration. So in the same way, sort of a seed grows. Once you find something that you're interested in, I think it will naturally follow the other steps. And when it comes time to sort of understand an algorithm, if there's a data set that you've created, if you have a question and you define the features and then you figure out how to generate the data for it, when it comes time to choose an algorithm, I think you'll be able to orient yourself much better through the different choices. And even if it's actually as instructive which ones don't work for you as which ones do, you can learn as much about them in that process. And then if you come back to them a second time with a different question, maybe there's one that didn't work before that now works for you, and you learned about it though previously, even though it wasn't the right candidate. Another question is Perl a good language for data analysis? And I think absolutely, emphatically, yes. And the reason for that is the core algorithms probably won't be written in Perl, but there's so much work that needs to be done around the algorithms in terms of preparing the data, and then also the integration side of it, that Perl is a great language for munging data. You have a lot of work going on in CPAN in terms of connecting to databases and putting pieces together. So in terms of doing data analysis, there's so much work that needs to be done besides just doing the actual modeling, that Perl is actually an incredible language for data analysis. And if it can even be queried over HTTP, it's not even an issue at all, and a lot of them do have Perl bindings. So start with what you know, and Perl is a good place to start, and there is work on CPAN. If you look in the AI : namespace, you'll begin to find things. Ken Williams has a couple of different pieces of work that he's put up there, so it is a good place to start. And you can work with what you know and branch off into other languages. So, and at the end, you might grow into a tree. Resources, machine learning with R, data mining, introduction to statistical learning, applied predictive modeling. The last one might be a little bit heavy to start with, but it was written by a guy named Max Kuhn, who's done some good work with R. Publishers, Pack, Morgan, Kaufman, and Springer. There's also one thing I learned by doing a Kaggle competition is that there's a huge social component to machine learning. The R language has the use R meetups. You could also look for different ones, but this isn't really the lone genius, in a room doing this by himself. Sort of iron sharpens iron, and participating in forums or meeting other people or talking to them is actually a really important way to do this. There's a lot of little tricks and learning that can be shared. So reaching out to others, I think, is really important in learning. Languages, I want to mention there's a language called Julia. It hasn't really, it's known, so it's not a total unknown one. It's not sort of totally above radar, but it looks like it's an up-and-comer in in statistical modeling, or whatever you already know. Data, another really important thing is where you actually get a data set to begin working with. It is helpful to define features and try and figure out how to generate them, but sometimes you do need to start with a pre-existing data set. So our government has a lot of, whether it's the US government or the Canadian government, there's a lot of usually information available there at many levels, local, regional, and national. A lot of websites have data that they'll make available. There's repositories. And then also your own life. I was speaking to someone before the conference who was working as a system administrator and wanted to look at network traffic. You have a lot of data going on in your own life. It could even be interesting to kind of predict what what wine would you like, or what sites would you like to visit. You have a lot of data in your own life that you can use. There's just standalone programs. These are some of them. Suites. It probably isn't important to learn a language like R or Weka. You can do it. I'm just going to run through the images. I use Creative Commons for all these, so these are just my kudos to them for sharing with me. Thanks.
Any questions? Why didn't you mention Python?
I did. I mentioned it in scikit-learn. Tell me more about your question. When you say why didn't I mention Python, why didn't I mention it as a good language, or why didn't I mention it? Why are you wondering why I didn't mention it?
Python is very heavily used in Toronto and even in this company.
Yep. Okay. So for me, I don't know Python, and I found Perl has been good enough for me in terms of getting going. So, but I didn't not mention it because I think it's irrelevant. There are a lot more machine learning packages for it. Scikit-learn is the one that seemed, when I searched, that people seem to recommend the most. So also Perl has the Perl data. I can't remember the acronym for it. It's
PDL.
PDL, yeah, Perl data. So anyway, so Perl does have PDL, but doesn't seem to have as much life around it, whereas Python is a lot stronger in that area. So yes, if you do know Python, you can have a lot more already available to you. But I guess one of the points I wanted to make is you don't necessarily have to learn. I was assuming this is a Perl group, and if you know Perl, that can be a good enough place to start. I think you'd probably have time better spent learning R than you would Python. If you don't know either Python or R, I'd recommend learning something like R first, but that's just my bias in terms of what I know.
Any other questions?
William, you talked about the Kaggle competitions. What exactly is a Kaggle competition?
Okay, so Kaggle is an organization that's trying to make data science into a sport. So there's recently one on data telematics where they gave you a huge data set of the GPS coordinates of different drivers, and they asked you to predict which ones were and were not. For every driver there were 200 trips, and of the 200 trips there were an unknown number that were not by that driver. So they were asking you to predict which ones weren't actually by the driver. And the first place team would get $15,000, the second one would get $10,000, and the third place would get $5,000. So it's basically a website that, not all the competitions have bounties, but it's a website that's sort of trying to turn data science into a competitive sport. At the same time, there's a lot of collaboration that goes on there on the forums. So you get real data, you get other people to work with, and then if you do really well, you could earn a prize. So it's Kaggle.com, Kaggle.
Are you having any lag issues on your end, William? You've turned into a badly dubbed Japanese movie because your mouth moves and then the sound comes.
No. In my Hangout, I appear clear. I'm not. Is it still there?
Yeah.
Oh yeah.
It looks fine to me, actually.
That's okay. We still understand you. The suggestion is to start moving your lips before you speak.
I could be a ventriloquist to myself.
Any other questions? No? All right. Well, I just want to say thank you, William. Much appreciated. This has been fantastic.
Thank you. Thank you all for listening. I appreciate the chance to speak to you.
Last chance, folks. Any questions online, off? No? All right, cool. Thank you very much. So this talk was a Hangout on air, so it will be archived to YouTube. So if you missed any of the links, you can grab the YouTube and you'll be able to fetch it just fine. Yeah, thank you very much. Oop, you already gone, William?
Yeah, he's gone.
All right, cool. Thank you very much.
Will you share the presentation itself?
Oh yeah, it'll go onto YouTube and we'll post it to the meetup. Okay. All right, thanks very much, Olaf.
All right, thanks, guys, and we'll announce next month's talks shortly, I guess, right?
Yes. I have 2 people in this room already pinned down and 1 more, I believe, to give a short lightning talk as well.
Perfect.
All right, thanks a lot.
All right, thanks, guys.
Cheers.